So I committed the cardinal sin of computer programming, and that is that I made my own programming language. It's generally considered a really bad idea. That's because it's hard enough to onboard someone to your project as is. They have to learn a new team, new tools, new code base. If you add a new language on top, it's only adding more fuel to the fire. And I totally understand that. It's like learning calculus and Spanish at the same time. Like me not knowing Spanish makes calculus so much harder, everything about it. And it's nothing to do with calculus, it's just that there's a language barrier, quite literally. So that makes sense. There's a lot of downsides to consider, and I don't think it's for everybody. I'm not saying that everybody should do this, but I did want to talk about why I did it, because I've been using this programming language for over a year now, and I am dramatically more productive, and my products are way better. In 2 weeks, I was able to make a demo that got me in the finals of a pitch competition with over 100 companies, and I was able to get into the hardest accelerator in the world, the Launch Fund. 20,000 applications a year and only 7 get in. It's the lowest acceptance rate of any accelerator. And you know what? No one really cared about the language. They cared about the product and the demo. Our customers run our software. They're only concerned with the functionality. It's the programmers that are concerned with the language. And we really started to see this with microservices. People were like flame warring online and all this stuff. But once we got microservices, what we noticed is we had these teams. There's Ruby people, and there's Python people, and there's Java people, all at the same company. Netflix was the first to the race here. And what they had to do is they started hiring mediators to basically negotiate between the teams because they just couldn't get along. Whether we like to admit it or not, language, we have really, really strong opinions on the languages that we use. And there's a lot of research that shows language pervades your thinking quite a bit. This is with natural language, but also with programming languages, because they have constructs, they have cultural tones, they have all this history, and there's certain things that are inexpressible in some languages and very expressible in other ones. So they've just become this kind of mental framework for everything that you're doing. I only want to talk about how important language is, not that my language is better or anything like that. So I understand the jokes that people make online. If someone wants to make a universal language and everybody should use this, and this is the way everybody needs to program, we go from 14 to 15. You're just adding +1 to the counter of languages. You're not solving the world, the universe's problems. That's not what I'm trying to do here. I am just trying to point out how important this stuff is. So what do I do, and what is the problem I was trying to solve? I do artificial intelligence, and specifically I do AI code gen. So I want to talk about this concept in AI that is long gone to history. It's almost forgotten to time. So in 1910, this is Alfred Whitehead. He wrote a book called Principia Mathematica. And what's really interesting about this book is that he started to formalize mathematical notation. And what it inspired people to do was start doing like math on top of math. So like not only just manipulating numbers, but manipulating the notation itself, like math that makes more math or math of math. Sort of like a higher order mathematics. And what this did is it inspired people to eventually coin the term artificial intelligence. In 1956, this group of scientists got together at Dartmouth, and they were doing much the same stuff that Whitehead was talking about, except they were doing it with computers because we had this new technology, and that's where artificial intelligence was actually coined by John McCarthy in 1957. And so John McCarthy and Marvin Minsky actually ran this cohort of people. There's some really notable names in here. Like one of them is actually, this is an homage to Claude Shannon. That's what Claude from Anthropic was named after. And this team came up with every single paradigm of artificial intelligence that we know today. They even came up with the precursor to neural networks, which is called the perceptron. In fact, Marvin Minsky, who's actually a huge contributor to the perceptron, also made an article about the limits of the perceptron and how it's not all encompassing. That's why this team looked at every single paradigm. They didn't want to just look at 1 or 2 ways to do AI. They wanted to think of every way to do AI. So they were exploring quite a bit. And it's the 50s. So this was a really good time to do it. It was a very exploratory time in history. And if you want to learn more about these paradigms, they're not really well understood today, but the director of research at Google, Peter Norvig, talks about this a lot. He is a big fan of symbolic computation. He talks about it a lot on his website, norvig.com, and he wrote a book that has a bunch of programming examples that are really easy to understand and go through, so you can actually play around with this stuff. And he just made it super, super easy. So I would highly recommend checking out that book if you want to understand AI for real. Now, post the 60s, unfortunately, all this stuff kind of died out. It's not really talked about. Not a lot of people know about all these different paradigms. That's because the money from DARPA, Xerox PARC, Bell Labs, it all dried up. We had to put our money into money-making things. We couldn't just be spending all of our time researching things that might not actually amount to anything. Now, we knew that it was going to amount to something eventually because we have the hindsight bias. We have the privilege of being in the future. And so we know that AI dramatically exploded since then. But at the time, there just wasn't a way to justify it. And so all this stuff kind of died along with the money. But not all hope is lost. Symbolic programming is still practiced by a bunch of very, very notable programmers. That book, SICP, the blue one, is actually, it used to be MIT's Computer Science 101 required reading. They since done away with it, and I think that's part of a larger shift of programming in universities, more so about getting a job, being employable, and they teach computer science overall a lot less now. There's a lot less background and context and stuff like that. But all of these guys are very big on symbolic programming. It is still used today, but it is in a more limited form than it was even in the 50s. That's actually really interesting. So I don't want to actually talk too much about exactly what symbolic programming is, but I do want to talk about the power of this stuff. So we all know Paul Graham. He founded Y Combinator, the largest incubator in the world's first incubator, longest lasting and most successful. Before he did Y Combinator, he actually made a startup of his own called ViaWeb, and that's Yahoo stores actually. He sold this startup to Yahoo for about $50 million, and that's why he got the money to start Y Combinator. And he wrote an essay that actually talked about how he was so successful with ViaWeb. And this is actually a really, really big piece of Paul Graham's thoughts. If you go through his essays, he talks about this concept in bits and pieces, but this one's entirely about it. And in Beating the Averages, he talked about how he had a secret weapon. And people must have thought that he was reading their emails, or he had like intel, or he was figuring out what they were working on somehow before the press releases. But no, he wasn't. He just read the press releases. And he was just so fast that it was unbelievable. And no one could understand how he was able to put out features so fast. And remember, at this time, Yahoo's the king of the world. They're the biggest company ever. They have all the money on the planet to build this in-house. But they still can't keep up with Paul. No competitors could keep up with Paul. He was making features with basically him and his co-founder at the rate of everybody else combined. And it didn't matter how much money they had. He was just super, super fast. Now, I don't want to talk about too much why his secret weapon worked. I want to talk about why it's hard to explain his secret weapon. So he talks about this idea in the same essay called the Blub paradox. And the Blub paradox boils down to, if you go up a power continuum, where at the bottom is machine code, at the top is the most high-level abstract language ever. If you are a Blub programmer, you are at a theoretical point in the middle of the power continuum. As you look down, it's really easy to see that those languages beneath you, so to speak, are redundant. And there's a lot of like repeated steps, and it's just kind of arduous. When you look up, it just looks weird and strange, and you don't understand it. So you look up, and it's just noise. You look down, it's very clear, but it's redundant. So Blub is the perfect language. And basically, everybody is a Blub programmer, because as soon as you understand another level up the power continuum, you're now at that level. And then so you can't look up anymore until you understand that thing. So no matter where you are in time, you're always at this point where you can look down, but you can't look up. And that's always the case. This is basically true for everybody all the time. And so I think I can make this a little bit more concrete with math. So if you look at the bottom of the power level of math, I could talk about a few numbers at a time. If I'm doing arithmetic, I could talk about a couple numbers, right? On a finite amount. If I go up the power level, I can do algebra, and I could talk about a universal set of numbers, and I say, oh, there's a pattern, it's true for an infinite amount of numbers. And so you could start talking about expressions on literally every single number all at the same time. That is a lot less redundant. You look down, you see somebody who's repeating the same steps over and over and over again. And then you look up, and if you're doing arithmetic and you look at like the first time you learned algebra, I'm sure everybody had this experience. You look at X's and Y's and equations, you're like, what the heck is going on? What is the point of this? There's just a harder way to do the thing I was already doing. I was already so good at this thing. But if you go up another level, you get into groups, and you're actually saying the same statement, but more universal. Because in group theory, this is abstract algebra. This is actually a little bit above algebra. So now we can talk about multiple kinds of math. I could talk about sets and matrices and linear algebra. I could talk about numbers all at the same time. And I could just say, okay, I have an operation. If I invert it, I get the original thing. Then you can go up again to category theory. This is basically the most abstract and most powerful known form of mathematics. And this can talk about basically every modality of math all at the same time. And in category theory, you're quite literally saying, if I do something and then I undo it, I did nothing. And that is true of proofs. This is true of computing. This is true of functions. It's true of sets, numbers. And it doesn't matter what the operation is. It's actually so abstract. We're just talking about all operations which you can undo them all at the same time. So I'm saying the same statement, but I'm getting wider and wider and wider in my applications as I go up the power continuum. And so this is the frustration that Paul Graham had. The frustration that he was experiencing was that you can explain algebra, you could explain arithmetic to somebody that understands algebra, but you can't explain algebra to somebody that understands arithmetic. So you can't translate from arithmetic into algebra, but you could translate down. You can't translate up the power continuum. It just becomes very, very hard if you're in a language that has things that are not expressible in this one. Then I just can't, there's nothing I can say in this language that will make you understand something in this language if there's certain things that just are inexpressible. And so this is the blood paradox. You can look down, but you can't look up. And so when people talk about abstract languages, I know where people's heads are going. When you think programming and abstraction, people go and talk about Haskell, and there's all kinds of guys online that are talking about how Haskell is the most abstract language ever. You talk about Lisp, maybe Prolog, stuff like that. And you might notice that none of these languages are actually used in the industry. None of them are like considered useful, right? So that is typically the rap that we get when we talk about abstraction. Now I'm going to just go pick on Haskell here for a little bit. I don't think Haskell is even more abstract than JavaScript. Like, what is there in, like, say, TypeScript? Is there literally anything in TypeScript that I can express that I can't express in Haskell? Or is there anything in Haskell that I can't express in TypeScript? Sorry, other way around. It's the same stuff. Like, Haskell kind of helps you. I think Haskell is useful guardrails. Like, I read this paper, Parsing with Derivatives. I used it to like help me teach me category theory. I thought it was like helpful as like training wheels, if anything. But there's like the citation at the bottom. It's like an advanced compiler's book, and they used Haskell to explain parser combinators. And I kind of loaded up the code and I played with it, and I started learning more about these functors, this extended functor family here, monads and applicative functors and all that stuff. And just kind of like playing around with it and implementing it myself. It helped me learn, but it's not more abstract. That's a lie. And actually, TypeScript's type system is better. There's like union type, there's real union types and things like that Haskell can't even express. So it's actually the opposite. So, but then in Lisp, this is actually going up the power continuum. I think this is a real level up, because in Lisp you can actually express things that are inexpressible in other languages. This is programs that write programs. That was Paul Graham's secret weapon, and I'm not going to explain what that means, because again, it's very hard to explain programs that write programs when you're familiar with like JavaScript, you're not familiar with Lisp. It's the blood paradox. So even trying to explain it without just like learning it for real is just, it's just an exercise in futility, basically. But if you want to be like a better programmer, I honestly think the 80-20 is just learn Clojure. Most Lisps are not used in production. Clojure is. I built my language in Clojure. Uncle Bob is a Clojure programmer. He made every single buzzword on the planet: TDD, clean code, agile. He's a Clojure programmer now. There's a lot of notable people that are actually doing real things that use Clojure. So if you want to be a better programmer, I think that's the quickest way to do it. Just do that. You can ignore everything else I'm saying. But here's another level up. Logic programming is another genuine rung up the ladder. Because in logic programming, it's symbolic programming still. It's still in that symbolic realm. But this time, the symbols represent solutions to problems. And so all I can talk about is the problem. I am not allowed to talk about the solution. The system does the problem solving for me. I can have it solve Sudoku puzzles. I can have it do arithmetic. I can have it do all kinds of things. But the point is, I'm not allowed to come up with a solution. I can only express what does it need to do. It is extremely declarative, much like a database is declarative. And we kind of know from like SQL and stuff what that means. So this is our secret weapon. It's logic programming. I made a logic programming language. That was the big reveal. Ta-da. So we don't use any algorithms in our code base at all. I haven't written an algorithm in a year. The technical logic's invisible. I focus on business problems only. And there's all kinds of difficult stuff in programming to think about. If you've been in a large code base, you start thinking about the knapsack problem. You start thinking about identity and access management, the CAP theorem. You start thinking about data warehousing. And this stuff gets really, really complicated. Anybody that's worked in a large enterprise architecture knows how painful this is. And sometimes doing something really, really simple, like showing the user their birthday, can literally take months because it's so much coordinated effort. There's so much complexity in the system. There's actually like a really funny YouTube skit about like showing the user their birthday, and it takes like 3 years because their microservices are so complicated.
I'm still not understanding this. Why is it so hard to display the birthday date on the settings page? Why can't we get this done this quarter?
Look, I'm sorry, we've been over this. It's the design of our back end. First we have to call the bingo service. See, bingo knows everyone's name-o, so we get the user's ID out of there. Then from bingo, we can call Papaya and MBS to get that user ID and turn it into a user session token. We can validate.
It's very funny, and it got like 4 million views. And that's because so many people know how those meetings go down. It's very satirized, but anyone that's been in one of those meetings, you can watch it, and you know it's kind of a joke, but that's exactly how they go. So it's very painful, and it gets very complicated. And here's the other thing about logic programming is this was the stuff that's lost in the 1950s. However, everyone kind of thought that it was too slow. No one thought that this stuff could go in enterprise. So we have logic languages, we have Prolog, we have Minicameron, and they're not used in real software. So if Clojure is trying to take Lisp and make it enterprise grade, this is what we're trying to do. We're trying to make Prolog and all these logic languages and make it enterprise grade. How do I take this idea and make it pragmatic? How do I make this so that I can use it to actually make money, service customers, solve problems, get it out of that academic sphere? So this is the secret. It is relational algebra. Our language is incredibly fast. It's faster than any code you'll ever write. And the reason is the same reason that databases are faster than any code you'll ever write. Because when you ask a database a question, it's also declarative, it's also relational. You form a query or a question, and the database figures out the answer. But you, when you're querying a database, are not allowed to tell it how to get said answer. What it does is on the fly, in the span of microseconds, it will look at all the tables, all the indices, and the size of all the data inside of those tables, and it will come up with an algorithm on the fly. It'll do it in microseconds. So it'll say like, oh, this table I'm going to scan, this one I'm going to make an index, I'm going to make an intermediate table here, I'm going to join these, and I'm not going to join this one right now. And it comes up with a really, really complicated query plan. That's what they call it, but that's the algorithm. And if you actually like analyze this stuff, if you ever use one of those tools that shows how is a database solving your problem, it's coming up with insanely complicated, sophisticated, contrived algorithms that no human being would ever write. And it's doing it in microseconds. And of course it's faster. It has to be faster. The reason it has to be faster is because if you're using a lower language on the power continuum, then you're using a fixed algorithm. That's one thing they all have in common, even Lisp and symbolic languages. Even if you're writing code that writes code, that code that is written is a fixed algorithm. It's like one finite thing. But in a relational paradigm, it could be any algorithm. And it could depend on the data. And if there's twice as much data tomorrow, then it might change it. It's always dynamic. It's always changing. It's always looking to see what's the algorithm I need right now for this very specific use case. And if you're lower on the power continuum, you can never do that. That is something that is inexpressible. And there's some other cool things about this language as well that I just kind of noticed. This actually was kind of an intent. I was almost going to say it's an accident, but this is just something that I'm actually surprised at how useful it is, which is this like scratchpad oriented programming that I can do. I always have access to my data all the time. I can query anything that I want. My data and my logic, I can go and prod and poke, and I can debug things live. That is just such a fun thing to do. And also, this is completely pragmatic. That has been a very core focus of this language, is to do enterprise things and to think about what are enterprise best practices and how do I make logic programming just take care of that for me. So I made an app. This is our app. We're a code generation tool, and it does data pipelines. It does all kinds of business things. It's very business oriented, so very non-academic, right? And the code that we generate actually blows our customers away. So we're in a similar experience that Paul Graham was at with ViaWeb, which is that no one can believe what it is that we're doing. Our customers are frustrated with Copilot and Cursor and Windsurf and all these things because they really just genuinely don't work. They just produce more bugs. They produce more churn. And they need more of a robust system built around them. They need more of a framework. This is what we provide. We have an operating system. We call it a generative operating system because it builds itself. And that framework, the more we build that out, the smarter our AI becomes. It becomes part of a broader system. And so this is what's blowing our customers away. They just can't believe what we're doing here. So if you're interested in what we do, a generative operating system, book a call with us. You can ask us about it. But it's basically picture a business suite like Oracle or Dynamics or whatever, but it builds itself with AI. And actually, I'll show you the app really quick. So this is what it looks like. I'm building a really complicated data pipeline right now. I can add like text and stuff. I can add my API keys. That's all well and good. But what's really cool about this language is that this is entirely built with logic programming, and it is fast and it does work. And what I can do here is I can actually just get that exact page that I was just on. That was the page I just showed you. And you can even see that text split for new process, all that stuff that was on that app. This is the exact same page. And you can actually see the data that's inside of anything. If anything's like broken or something's not showing up the wrong way, I can just go grab that data right away. And I can go hotfix it if I wanted to. Now I have like deployment pipelines and stuff like that, but if I wanted to hotfix it, I could. So I already have a table ID that is predefined here. It's defined a little bit up in the query off screen. But what I can do is I can grab all the blocks on all the pages. And so I'm saying, here's block. If I join that on the table ID, this is just like what SQL does. This is like a database. I just did a join. And so now I have one specific block, and that's joined on everything else now. That's joined on the app ID, that's joined on the pages, the page index. I can say, what's the block and the block index. And I can just go grab all this stuff live and I can see it all the time. So that's the 12th element in the block or the page. That's pretty cool. And I can go look at my table, and this is all the same exact data that we're seeing on the screen. So my error, the code, the update triggers, all that stuff's in here. I can see my execution error. And so this is very, very live. It's very pragmatic. I can go hotfix anything, anytime I want. And it is just solving the query very, very fast. So we just don't think about the technical problems. We just talk about the business logic. So that's why I did it. And it was to build this generative operating system. So we're going very, very fast. We are doing code gen better than Cursor, better than Windsurf. And it is by a long shot. If you work with us, you can see that we can do things that normally take weeks or months, and we're actually doing it in days. The promise of code gen with artificial intelligence is that you can get dramatic productivity gains. But we're not going to get that by just making the AI 10 times smarter. I don't even know if we can. But we can make the system around the AI 10 times more robust. And the way we're going to do that is by being able to develop features faster and being able to access higher leverage things. So that's basically it for this video. If you're interested in meeting our team or utilizing some of this stuff, if you want to learn about this more or you want to incorporate it into your business, that's what we do. We're all about optimizing business. We're all about business-facing needs. So feel free to book a call. Thank you very much.